Hello everyone, welcome to week 5. So what we'll do this week is we'll learn one more method for finding deflection of statically determinate beam, which is conjugate beam method. Then we'll briefly review the concept of bending moment and shear force diagram in frames. We have already done that for beams, and then finally we'll determine the deflection for beams and for frame via virtual work method. So today we'll start with deflection of beam via conjugate beam method. Okay. You see, suppose let us first give you the basic or let us first set the platform to derive the concept for conjugate beam method. You see, suppose take any beam. In this case, it is simply supported, subjected to some loading. Okay, but whatever that we will see, the concept is same for any boundary conditions and any loading pattern. So suppose this is a beam we subjected to a distributed load like this. Then what we have done so far, we know that the bending moment. Suppose this is the bending moment diagram of this beam. Now, as far this loading condition is concerned, the beam will deflect downward. So the beam will sag, which is according to our sign convention positive. So this is positive bending moment. We also know how to draw the shear force diagram for this. So this is the shear force diagram for this. This is a typical representative bending moment and shear force diagram for this kind of loading condition. Okay. Now, so we know how to do that. Once for a given problem, we know how to draw bending moment and shear force diagram, and this step is called statics. Okay, for a given problem, determine the internal forces. Now, when from this to get the internal forces, the what plays a major role is the equilibrium equation. So we use the concept of equilibrium, static equilibrium, to get these internal forces, right? Now in this, what are the variables we have? The static variables are the applied intensity of the load Q, bending moment M, and V shear force. The bending moment and shear force may also change with length of the beam, but for a given beam, for a given length, these are the parameters which can influence the bending moment and internal forces. So this in this entire step is statics. Our static variables are this intensity of the load, bending moment, and shear force, right? Now this is not the only thing we want. What we want in addition to internal forces are deflection of the beam. Suppose this beam deflect like this, okay, and what we want in addition to the internal forces, we want what is the deflected shape, how the deflection changes with s, then what will be how the slope changes with x. So this deflected shape also we want to determine. Okay. So this is, if you remember, this is from the internal forces from safety point of view, and this is for the deflection from serviceability point of view. So these are the two responses we want from a given from structural analysis. Now from this step, once we know the forces on the beam, internal forces on a structure, and from that internal forces and the determine the deflection, this step is called kinematics. Kinematics essentially is the branch which where we determine the motion of an object as a relation with the forces that causes the motion. In this case, motion means the deformation or deflection of the beam. Okay. So this step is called kinematics, and what plays a major role in kinematics is the stress strain relation or load deflection relation. We know how these internal forces are related to deflection, and for in this course we assume it is linear elastic stress strain relation and obeys Hooke's law. Now what are the variables in kinematics? The variables are, if you look at this figure, what are the things we want? We want the at a given particular point, we want what is the deflection of that point, what would be the slope at that point, and what would be the curvature of the point. Curvature is 1 by rho, it is rho is the radius of curvature. So, we want the curvature, slope and deflection of the point. Okay. So, these are static variables and these are kinematics variables. Is there any relation between static and kinematic variables, and have you studied that relation? Yes, we have, you see, and that relation is the elastic curve. Okay. So, elastic curve, the equation for elastic curve gives you how the internal forces varies with the deflection, or in other way how the static variables related to kinematic variables. And if you observe from the last week, whatever method we studied in determination of deflection of beams, in most of all the methods are essentially it is a sum. All the methods, the premise of all the method is elastic curve. They use the equation of elastic curve in a different way. Now, so this was we have done directly integrating the elastic curve. We have also done the moment area method, which is another interpretation of elastic curve, and the method that we are going to study today is conjugate beam method. Now, before I introduce conjugate beam method, you see there is a similarity between the static variables are related to each other. And the kinematic variables are also related to each other. Means rho is related to theta, and then theta is related to y. Similarly, q is related to moment, and moment is related to shear, and all these variables are related to each other. Now, what we can see, there is a similarity. There is a very interesting similarity between the way static variables are related to each other and the way kinematic variables are related to each other. And the conjugate beam method is essentially the makes use of that similarity. Now, just to make it clear, suppose let us recall the equations for static. We already derived this equation, that shear force, how shear force is related to bending moment. And if you remember, in all the bending moment diagram, we observe the bending moment is 1 order higher than the shear force. So, this we derived already, and we also have another relation that dV dx is equal to minus q. Q is the intensity of the load on the beam. So, this is how shear force related to intensity of the load. These are all static. So, V, M and Q, these are all static variables, and these are the way the static variables are related to each other. Now, let us see what happens to kinematics variable. We know theta is equal to dy dx, that is our definition of slope, and then we also derive that how the d theta dx is equal to curvature. Remember, this minus sign is because the curvature and moment are, if the curvature increases, the moment decreases, or the moment increases, curvature decreases. That is how our sign convention is. That is why this negative sign. Now, so this is theta, y and rho, all 1 by rho. They are the kinematics variables, and these kinematic variables are related to each other like this. Now, let us see what are the similarities. Now, if we say V is equal to dm dx, suppose say V, if we see how V is related to m and how theta is related to y. Now, V is equal to dm dx and theta is equal to dy dx, and this. So, if we take V as static variable and it is related to static variable m, the way V related to m, theta is related to y in the same way, isn't it? Now, let us see Q is the if again V, how V is related to Q and how theta is related to curvature, that is also very similar. So, what we can say, the shear force is the first derivative of moment, and here theta is first derivative of deflection. First derivative of shear force is intensity of the loading, first derivative of slope is equal to the curvature. Now, if we combine these equations, static equations and kinematic equations, and define a general equation like this. Suppose if we define an equation like this, where three variables psi, phi and capital Phi. Psi is equal to del phi d phi dx and d psi dx is equal to minus phi. Now, you see this is the general equation which can give you both relation, the static, these relations as well. For instance, for static case, if phi, psi and small phi, they, if that is replaced by q, v, m, the kinematic, the static variables, then this equation is static equation. Similarly, if this phi, psi and small phi, they are replaced by the static variables, then this equation gives you this equation. So, this is the general equation which gives you static and kinematic equation depending on what psi, phi and capital phi are chosen. Now, what point I want to make here? You see, means if q is replaced by 1 by rho, then V, the shear force, will be replaced by theta, and similarly moment will be replaced by y. Or in other way, suppose if we have two systems, it is system 1 and this system 2. Okay. Now, in system 1 our variables are q, v and m, and in system 2 variables are curvature, slope and deflection. And we also know that how these variables are related to each other, and the same way these variables are also related to each other, right. Now, now in system 2, in system 1 or in system 2, suppose, or say in system 1, suppose if q is replaced by curvature, okay, if q becomes curvature, then curvature of system 2, then automatically the shear force of system 1 becomes slope of system 2, and the bending moment of system 1 becomes deflection of system 2. Means, I repeat once again, if intensity of the load in system 1 is replaced by the curvature of system 2, then the shear force of system 1 gives me the slope of system 2, and bending moment of system 1 will give us the deflection of system 2. Now, in this case it is called that system 1 is conjugate of system 2. So, how this conjugate is obtained? Conjugate is obtained by replacing q by curvature of system 2. So, only thing we have to do is, in order to get the conjugate system 1, we have a system 2. Now, in order to get the conjugate system 1, what we have to do is, we have to replace the intensity of intensity q by 1 by rho on the curvature of system 2. Now, if we do that, then what we have to do, we determine the internal forces in system 1. Internal forces are V and M. So, since the 1 by q is replaced by 1 by rho, internal forces in system 1 will give us other two kinematic variables of system 2, theta and y, and this is conjugate beam theory. Let us demonstrate this through an example. Now, suppose take a simply supported beam which is subjected to uniformly distributed load. We have seen this problem several times. Now, the bending moment diagram of this beam is this, and we know the bending moment, how the change how the bending moment changes with x is this. Okay, we have already seen it in various places. Then, so this is now consider a system. So, this is the bending moment diagram for this system. Now construct a system where the same length of the beam, same dimension, everything is same, but the load on this beam is replaced by m by ei diagram of the real system. Okay. And if we do that, so this is the real beam, this is the bending moment diagram of the real beam, and this is the conjugate beam. Now, what the problem reduced to? Now, initial problem was determine the deflection of this beam. Okay. Now, instead of directly computing the deflection of this beam, what we have done is we constructed a conjugate beam where the length is kept same, only the load on the beam is replaced by the bending moment diagram divided by EI, and then what we have to do is we have to find out the shear force and bending moment of this system, because shear force of this system will give us slope of this system, and bending moment of this system at any point will give me the deflection of this beam, deflection of this system at that particular point. Okay. Now, this is conjugate beam method. Now, let us see, suppose now this is the conjugate beam where the in real beam it was initially uniformly distributed load. Now, in conjugate beam the load is replaced by the bending moment diagram, bending moment by EI. This was the bending moment M by EI, how the M by EI changes with x, and we also know that the maximum moment is QL square by 8. So, this point becomes QL square by 8 EI. Now, let us draw the free body. Now, only thing is we need to find out the internal forces of this. So, a problem of kinematics now is translated or formulated as problem of statics. Okay. Now, here we need to find out what are the internal, which is much easier. Determination of internal forces probably the easier than finding out deflection and slope in a structure. Now, so draw the free body diagram of the entire structure. So, this is hinge support. So, automatically these are the two forces, and then the roller support one forces, it's one force. So, this is the free body diagram. Now, if we so this is the total Q. Total Q will be the area of the entire this parabolic distribution, and the Q will be integration of fx between x between 0 to L, and if you do that, this will give us so either you can do directly do the integration, or we know the expression for parabolic area. So, this is 2/3 of this length into the length, this will give QLQ by 12 EI. So, this is the total load on this. Okay. Now, so if we do if we apply the equilibrium condition on the free body diagram of this, so summation of fx is equal to 0 automatically gives us Ax is equal to 0. Summation of Ay is equal to 0. Summation of Fy is equal to 0, since it is a symmetric beam. So, Ay will be equal to Bi, and Ay equal to Bi will be Q by 2, total load divided by 2, it will be shared by both the support, and this will give us QLQ by 24 EI. This is the total Q we already obtained. Okay. So, these are the support reactions. Okay. Now, so these are the support reaction just now we obtained, right. Now, this is the total Q. Now, suppose I want to determine what is the bending moment and shear force at that point at the midpoint. Okay. How to do that? We take a section at the midpoint C and draw the free body diagram of this part. Now, if we draw the free body diagram of this part, so this length becomes L by 2, this is QL square by 8 EI, and this is the moment and this is the shear force. Please note the sign convention what we are using for moment and shear force. Moment is sagging moment positive and clockwise couple, shear is positive. There will be ideally there will be a horizontal force as well, but since Ax is equal to 0, that is why it is not explicitly shown here. So, it will be anyway 0 axial force here. Now, let us apply the equilibrium condition on this beam. Take summation of moment at C is equal to 0. So, what it gives us, what are the contribution will be from MC, then which is anti-clockwise, then contribution from AY which is clockwise, and contribution from the external applied load which is again anti-clockwise. So, MC is anti-clockwise minus AY will be the contribution of AY will be clockwise, that is why it is positive, and then contribution from externally applied load again is anti-clockwise, that is why it is negative. So, this gives us MC is equal to this. Okay. Now, what we have, shear at A is equal to the support reaction at A, which is equal to QLQ by 24 EI, that we already obtained what is the support reaction. What will be the shear at B? Shear at B will be minus this will be minus By, not AB. Okay. Shear at B will be minus By, which is why it is minus, because that is what our sign convention is. Because if we take our sign convention is shear which produces clockwise couple is positive. Now, but By is taken upward positive in this here, that is why shear will be minus By, and this is equal to minus QL cube by 24 EI. Please, again and again I am telling you, please be careful about the sign convention. Okay. And also we have just now obtained the moment at C is equal to Q 5 QL cube by 384 EY. This will be again 5 QL to the power 4, not cube, L to the power 4 by 384 EI. Please correct it. Okay. Now, from the real this is the real beam, and what results we have if the real beam deflects like this, and this is theta, this is theta b, and this angle, this distance is delta c, deflection at midpoint. Then we have already seen these examples through other methods, and we have these results that theta a is equal to minus theta b is equal to QL cube by 24 EI. Theta a is positive because it is clockwise taken, and theta b is taken anti-clockwise, that is why negative. This is consistent with the sign convention that we use for bending moment and deflection. And what is delta LC? Delta C will be 5 QL to the power 4, again please correct it, it will be L to the power 4 by 384 EI. Now you see, can you see the similarity? Can you see the same? This is the real beam and this was the conjugate beam. Now you see the shear force at A is equal to theta A. Shear force at A of conjugate beam gives you slope at A of real beam, and shear force at B of conjugate beam gives you slope at B of real beam. Please check this. And then another thing is bending moment at C of conjugate beam gives you the deflection of real beam at C. So, the thing is the method is then method is essentially suppose for a beam we need to determine the slope and deflection. What we need to do is, first we need to construct a conjugate beam, and first step of constructing a conjugate beam is replace the load on the conjugate beam by the M by EI diagram of the real beam. Okay. We will see other aspects of making conjugate beam as well, but just as of now the definition of conjugate beam what we have as of now, replace the load on the conjugate beam by M by EI diagram of the real beam, and then instead of finding the deflection and slope directly of the real beam, determine the bending moment and shear force diagram of the conjugate beam, and bending moment is conjugate to the deflection of the real beam, and shear force of conjugate beam is a conjugate to slope of the real beam. The problem of kinematics is now represented as or formulated as problem of statics. Now, before we go further, you see, we know how to draw bending moment and shear force diagram of a beam, right? My advice is, do not the first is, suppose you are asked to draw a bending moment diagram of a given beam. Okay. Now, before you actually compute the bending moment diagram, before you actually use your pen and calculator, try to understand how for that particular loading condition, for that particular support condition, how the beam may behave, may deflect, and in your mind try to draw the bending moment and shear force diagram before you actually compute them using calculator, using the concept of structural analysis. Okay. Now, if you do that, that will help you to that exercise will help you to understand or to have a better sense of structural behavior of structure under different loading. Now, reverse is also true. Reverse is, suppose a bending moment diagram is given to you or a shear force diagram is given to you, right? Now, just by looking at the bending moment diagram and shear force diagram, we should be able to say something about the loading condition of the beam, support condition of the beam. Okay. and that exercise is also important because it will develop the sense through which we can understand the structural behavior without actually doing any computation. Now, in the next here what I am going to do is, suppose we have already discussed the part of conjugate beam. Again we will go back to that. This is important for the next part of conjugate beam, the concept of conjugate beam. Suppose this is a bending moment diagram given to us. Okay. Now, what this bending moment diagram tells you, that suppose it is also known that we have a support at A and support B. Now, bending moment is 0 at support A, bending moment is 0 at support B. So, this is the support condition of the beam will be, support condition of the real beam will be, there will be no constraint against rotation. So, naturally it will be hinge support and it will be roller support, or this is hinge support, this is roller support. Okay. Now, what is the loading condition? Loading condition will be, since it is linearly varying, the bending moment is linearly varying between these 2 points. Bending moment linearly varying means the shear force between this point to this point will be 0, because that is what shear and bending moment they are related to each other. Shear is 1 or less than bending moment. Bending moment linear means shear is 0. Okay. Now, and then so between these 2 points to this point there will be no external load, and then again bending moment then decreases like this. So, again we have a some load here, and between these to this point there is no other load. So, but just by looking at this bending moment diagram, we can say that this would be this is the probable real structure. Okay. As of now, what we have done is, this structure is given and we determine the bending moment and shear force diagram. What I am telling you to do is the inverse thing. You know the bending moment diagram and try to identify what the problem or what the structure is. Now, let us take another bending moment diagram. It is again similar to this, but then we have another, it is a simply supported beam. We have one load here and that should be another load here, and not only that, since now the bending moment decreases after reaching this point, bending moment decreases, this value is lesser than this value, we can also say that P1 should be greater than P2 or P2 should be less than P1. So, again by looking at the bending moment diagram, we can comment on the structure. Now, let us take this problem where bending moment is linearly varying and then become constant. Now, since here bending moment is 0, so it will be either this support will be either hinge support or either free support. Since we have a non-zero bending moment here, means either we have a externally applied moment or the support is fixed support. So, this could be this could be the beam, and the loading condition could be like this, because this is constant. So, since this is constant bending moment, so this is the loading condition we may have. Similarly, for this, if your bending moment diagram is this, then probably the loading will be something like this. Okay. Now, similarly, if we take another case, a bending moment diagram is like this, and then probably the loading condition on the beam will be like this. Okay. If it is symmetric, that is why it is the uniformly distributed load. Now, if the bending moment diagram is parabolic but not symmetric, probably our bending moment loading condition will be like this. Okay. Or any other distribution, but not regular, not uniform distribution. Now, this is interesting. Suppose our bending moment diagram is this. What it tells you, the bending moment is 0 here, bending moment is 0 here, and bending moment is 0 here, bending moment is 0 here. Okay. Let us see what would be the, so suppose it is known that point A and point B is supported. So, since at point A and at point B there is no bending moment, so it will be hinge support. Okay. Now, then since the bending moment is 0 here, what it tells you that we have we may have a hinge here. Okay, because at the hinge location bending moment is 0, and we since then bending moment reaches a peak value and then decreases, we have either some externally applied load or support at this point. Suppose we have a support here. Now, bending moment is parabolic distribution between this point to this point, and bending moment is linear and then linearly varying between this point to this point. What it tells us, we have an applied load like this, concentrated load, and on this, since it is parabolic distribution, probably we have a uniformly distributed load like this. So, this is the bending moment. This probably the real structure which correspond to this bending moment diagram. Similarly, if the bending moment diagram is this, where the bending moment is constant positive, constant negative, then your probably the real structure would be a bending moment applied here and another bending moment applied here, since it changes sign from positive to negative. Now, and also we know that in this case, since this M2 is greater than M2 is greater than M1. Okay. Now, so if we have bending moment diagram, and that is true for shear force diagram as well. If we have bending moment diagram and shear force diagram, then we can have we can get some information from those diagram. We can have some idea about the support conditions of the structure and the loading conditions of the structure. Now, but whether these support conditions and these loading conditions are unique or not, that I leave it to you. There could be, for all the bending moments I showed here, that could be for each bending moment there could be other structures or other support conditions or other loading condition that may give you similar bending moment. Okay. So, whether the real structure that we derived from the bending moment diagram are unique, that derivation is unique or not, that I leave it to you. But the essence is, don't just draw the bending moment diagram and shear force diagram. You should be able to read those diagram as well. You should be able to interpret those bending moment and shear force diagram as well. Now, since in conjugate beam method, even in moment area method as well, in this method bending moment plays a very important role. In moment area method, we saw that the bending moment, we have the bending moment diagram and the moment of that bending moment diagram and the area of that bending moment diagram will give you shear, slope and deflection. In this case also, the bending moment plays a very important role. So, in addition to just drawing bending moment diagram and shear force diagram, you do the inverse as well. Given bending moment diagram, try to identify the loading condition and the support conditions. Now, we will stop here today. And now, next class we have started the definition of conjugate beam. The definition of conjugate beam is not yet complete. One aspect of conjugate beam is loading condition of the bending loading on the conjugate beam will be same as the M by EI diagram of the real beam. Now, in the next class we will see some other aspects of conjugate beam and see the complete information and find out the complete information that we required to construct, to make a conjugate beam, and then see some examples how this conjugate beam concept can be used to determine deflections and slope. Okay, thank you.